So now we talk about limits for multivariable functions. Um, and with limits, I think it's nice to start with the easy case. So what's the easy case? So if a function is continuous and well-defined at a point, find the limit at that point is as easy as just plugging the point into the function. It was true for y equals f of x. It's also true for z equals f of xy. So here's a simple function, or here's a function x squared plus y over y. And we're going to find the limit as xy goes to the point 1 comma 2. So again, notice that these are functions of two variables, so we have to say what the value that each variable is, what its target value is. So now in this case, notice that in doing this limit, or dealing with this function, I should say, there is a potential problem. The potential problem is when y equals 0. However, that's not the limit that we're trying to find here. We're trying to find the limit with x's target value is 1, and for y the target value is 2. So we're not near any problem situations, and we can just plug it in. Okay. So that's the easy case. Easy case is now done. All right. So in the hard case, what do we do when, for example, typically we use limits when you can't just plug it in? Limits for multivariable functions are going to be much harder, and here's the reason. Instead of for y equals f of x, when x is approaching a certain value, there's only two directions from which it can approach. Imagine for x values, imagine we're on the real number line. There's only two directions for which it can approach, from the left and from the right, or from increasing and decreasing. Okay. What about in the two-dimensional case? So where the domain is two-dimensional. So think about the previous problem. So we had x comma y going to the point 1 comma 2. How can x comma y approach the point 1 comma 2? How many possibilities are there? Well, it could be coming from the left, it could be coming from the right if x is changing. Or y could be changing. It could be coming from the top, it could be coming from the bottom. Or it could be coming from some totally other orientation. So perhaps x is changing and y is constant. Perhaps x is constant and y is changing, or perhaps they're both changing. So basically, there's infinitely many possibilities. So in order to think about how to handle this, we're going to talk about limits in the same three ways we hopefully you previously considered limits: numerically, graphically, and algebraically. So first, numerical limits. So previously, to find the limit of a function of one variable, you made a list of function values, and you sort of looked at the space where it's undefined, and you said, what do I think the target value is there? So we're going to need a way to represent values for a function of two variables. So notice that we can't just have a column for x and a column for y. We need to represent x values and y values, every possibility, and then for each of those points, a z value. So for this, we're going to make a table, but it's going to be a bigger table. So let's consider this function with this limits, and we're going to go back to our table representation, which we've talked about before. So find the limit as xy goes to 0, 0 of sine of x squared plus y squared over x squared plus y squared. So notice, of course, that if you just plug in the values, you get sine of 0 over 0, which is 0 over 0, and that's an indeterminate form. So let's use our table of values to see what we think. So notice at the point 0, 0, it's undefined, so it's blank. And then every other point is defined. Now looking at the table, approaching this spot, what does it look like the z value is approaching? Or what does it look like the target z value is? What value, if we filled in there, would make a lot of sense? Well, just looking at all the numbers all the way around, everything is 0.97, 0.98, 0.99, 0.999. So pretty much by inspection, you can see that no matter how you get here, the value it's approaching for the function is 1. So using this numerical approach, we would say that the limit is 1. Now let's do another example. So let's find the limit as xy goes to 0, 0 of x squared minus y squared over x squared plus y squared. So again, the first thing you should always do with a limit is plug it in and see what happens. So plugging it in, we just get 0 over 0, which of course continues to be an undefined form. Okay. So now we're going to use our numerical approach. So for this function, let's make a table of values. So in this case, sorry, I left my little spreadsheet error message in there. So of course it's 0 at the point 0, 0. It's undefined, a little error message. Now look at the different ways that we can approach this point and notice the crazy things that happen with the function value. So what are some of the ways that we can approach and what are some of the results? So notice that if you take x to be constant, so x is always 0, and you approach as y is changing, you get -1, -1, -1. So from this approach direction, your limit's going to be -1. But now let's take another easy way, a straightforward way to approach, which is what if you take y is constant at 0 and x is changing, so we're approaching along this line, so your function values are 1, 1, 1, 1, 1, 1, so clearly the limit this way is 1. So already we can make a final conclusion about this limit, because we have an approach from one direction and an approach from another direction that gives us two different limit values. So just like with y equals f of x, we know we get two different limits from two different directions, therefore the limit is undefined. Now I also want to point out that there are other ways to approach that we can still see from the table. So another possibility is we approach along the diagonal. So visually, it just means approaching along the diagonal. Notice that what is the diagonal? Now it's a little skewed because the cells are not perfect squares. But the cell, go to x equals 0.1, 0.1. Sorry, the point is 0.1, 0.1, 0.2, 0.2, 0.3, 0.3. So this diagonal is the line y equals x. So if you approach along the line y equals x, you get 0, 0, 0 all the way. So the limit this way is 0. Same thing if you approach along that line from the bottom. You're getting 0, 0, 0, so the limit is 0. And then you can also skew it. You're going to do on the other diagonal. So y equals negative x. And again, all these values are 0, so the limit is 0. And there are other lines hidden in there, but we've got, at this point, we've got 8 different approaches, and that's pretty good for us. So now let's take a look at, okay. Oops, sorry, one more. So now I want to take what we're doing and let's write this down formally. First let me mention this. So for one variable functions, we need a two-sided limit. You can take each of those if they're equal, then the limit exists. For more variables, and we're only going to look at z equals f of x, y, we need an every-sided limit to prove that the limit actually exists. So proving limits exist is actually going to be hard. It's something we're not going to do. We're going to take evidence the way we've done so far. So let's take this So let's take this table example and let's try to write down some things. Okay, so here's the function. At the point 0, 1, it's undefined. If you plug it in, you just get 0 over 0. So let's use the table below and let's try to find some limits for f of xy as xy approaches the point 0, 1, coming along different paths. So let's take a look and let's develop a notation for limits here. So let's take the limits as xy goes to 0, 1 of the function, but now let's say where we're approaching. So what are some different ways that we're approaching? So one nice one is to say as x is constant. So if x is constant, we need x to be fixed at 0. That'll get us to the point 0, 1. So x is fixed at 0, we can approach this way. And doing that and look at these numbers, 0.66, 0.62, 0.58, 0.55, 0.52. And of course, there's our target point. What does the target value look like? Target value looks like it's coming in to be 0.5. So in this case, we take the limit along x equals 0. So that's the path that we're coming in on. And if we do it that way, the limit is 0.5. And notice that that's true whether or not we're coming in with y increasing or with y decreasing. So on each path, of course, we can come in from one of two directions. Okay. Now let's do another one. Let's take another simple one. Let's take y fixed. So with y fixed, y is fixed at 1, constant, and then x is changing. Now let's take x decreasing. So x decreasing means we're coming in this way. So 2, 2.5, 3.3, 5, 10. What does it look like is happening to the function value as we get to our target point? Function value is increasing. Now, what is it increasing towards? You can't necessarily see it from this table, but if we were to punch in some more, include some more precise values, we got x is 0.1. What if we did 0.01 or 0.001? You'd see the function value getting much bigger and much bigger. So what's actually happening there is that it's going to positive infinity. The limit as xy goes to 0, 1 along y equals 1, and in this case, x was decreasing. That was positive infinity. Now notice that along the same path, y equals 1, what if we take it from the other side with x increasing? We got -2, -2.5, -3.3, -5, -10. So in this case, the function value is negative getting smaller, 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 and it's blowing up, but in the negative direction. So in that case, the limit as xy goes to 0, 1 along y equals 1, but with x increasing, that limit of the function is going to be negative infinity. So this is a notation that we can use to write down these limits. First you say limit, then you say where your xy point is headed towards, but then you can also indicate the path that you were taking in order to get to your point. And of course, we can continue to take some other paths as well. So for another one is if we do on the diagonal, well, there's a nice obvious one on the diagonal through quadrants 2 and 4. If we come along there, that the value of the function is always 0, so the limit is 0. Now, of course, be a little careful about what the equation for that is. Notice that we're not going through the origin. We're going to the point 0,1. We're not going through the origin. So the equation for that, notice that the y-intercept on that is 1, and your slope is -1. So this is along y equals -x plus 1. That's the equation for that path. And notice that even if you can come from either direction and you get a bunch of 0 values. So either direction, that limit is 0. And there's again other paths you can take, but here we've got, let's see, two of these we looked at it from 6 different directions, along 3 different lines. Okay. And so that's the notation we can use. All right. So this was the numerical approach, where we're basically just looking at a big table of values and trying to see what the limit value is. We can also do limits graphically. Let's take a look. So here we're going to look at, I'm going to provide the graphs. So we're going to use the exact same 3 functions we just had, and I'm going to provide the graphs. So rendered using software. So once again, limit as x, y goes to 0, 0 of sine of x squared plus y squared over x squared plus y squared. So here is the graph of that function. So now looking at this, so it may not be super obvious, so just take a look to familiarize yourself. So x equals 0 is in the middle, y equals 0 is in the middle, and then the range of values depicted on this graph, at least, on the bottom you got z equals -1, on the top you got z equals 1. And what we can see is that as we head to the middle, we're sort of reaching the top of this dome. And it's hard to tell, it's always hard to tell with 3-dimensional graphs, but we're reaching the top of this box. So any way you approach, so the point 0, 0 is somewhere right around here. Any way you approach, we're reaching this top value of z equals 1. Okay. Now, of course, what you can't see on the graph is the fact that that point itself doesn't exist, so there's like an open circle there. But we know it's true. Okay, so that's graphically what that would look like. The other graph next. So our next one was limit as x, y goes to 0, 0 of x squared minus y squared over x squared plus y squared. So I'm going to show you the graph. This graph is going to be funky, so we've got multiple views. So yeah, this graph is bananas. So now let's take a look and think about what it means to approach from different paths. So notice that 0, 0 again is kind of in the middle, but depending upon which way we approach that middle, we're going to get different values. So notice that using the graph on the left, you can approach in a sense in the valley, and if you come on in the valley, you could see that path is x is constant at 0, and all the z values are going to be -1. Also, you could approach the middle, which is the point 0, 0, along the ridge. So coming in along the ridge, that's where y is a constant value of 0, and all your z values are 1, so the limit there is going to be 1. And in fact, what you can see is that depending upon how you approach, you can actually get any you can come in with any function value you like. You can approach any function value between -1 and 1. Now, what would actually help is to see if we could identify a path along which all function values are 1, or -1, or another constant. So we can kind of eyeball it from this one, but it'd be nice if the graph just told us that directly. So what graph tells you, what sort of graphical representation tells you directly, here are all the places where the function value is 1. Here are all the places where the function value is -1, et cetera, et cetera. So that is exactly the definition of a contour plot or a contour map. So now let's look at the contour map for this last graph. So here's the contour map for this graph with no limit. And now the contour map shows you explicitly that you can pick a path with a constant function value. So therefore that's going to be the limit as you approach along that path. Now it's laid out for you very easily. So next, let's look at the contour map for the first function, where the first function did have a limit. What did that one look like? So this one has a well-defined limit. What does the contour map look like? So for the function sine of x squared plus y squared over x squared plus y squared, notice that your point that you're headed toward is right here. And no matter what path you take, you are crossing contour lines in order to get to that point, and you're crossing contour lines as the values approach 1. If you come from here, if you come from here, if you come like this, it doesn't matter. You're crossing contour lines headed to the value of 1. So in some sense, the easiest way to do this is using a contour map. The easiest way to figure out limits is with a contour map. So now we come to calculating limits algebraically. So let's take this one piece by piece. So first of all, we know that the function, this limit is not defined. We already saw this with the numerical table. We saw this graphically. So limit is xy goes to 0, 0 of x squared minus y squared over x squared plus y squared. So in order to do this calculation, we're basically going to repeat as a calculation the same thing that we did both numerically and graphically. So what do? We're going to show that two different paths will give two different limits. So first, let's do this one. So first of all, limit as xy goes to 0, 0 along x equals y of this function. X squared minus y squared over x squared plus y squared. So what do? We simply, since we're along the path x equals y, we simply make that substitution. So that gives us x squared minus x squared over x squared plus x squared. And now the limit, since we've replaced y, it's just the limit as x goes to 0. We've eliminated a variable. And that's just the limit of 0 over x squared. And of course, that limit is just 0. Now we do it along another path. Take the limit as xy goes to 0, 0 along x equals 0, again of our function x squared minus y squared over x squared plus y squared. And then we take the limit along x equals 0, so we can just make that substitution. So now it's 0 minus y squared over 0 plus y squared. And because we've substituted for x, now we're just taking the limit as y approaches 0. Well, what is this? Limit as y goes to 0, negative y squared over positive y squared. Well, clearly that's just the constant -1, so the limit is just -1. And this is how we can actually do the calculation. So therefore, we can conclude that the limit of the function does not exist. So in this problem, we knew that we could take these two paths and we would get different values based on what we already saw with the numerical information or with the graphical information. So to find a limit algebraically, there's two options. So one option is if you want to, we can show that it's not well defined. The limit is not well defined by taking two different paths and showing that the limit along each path, you get a different value, so limit does not exist. What's the other option? We want to show that the limit is well defined. Well, to do that, you need to, in a sense, show the limit for every single path has the same value. So that's a hard thing that requires techniques beyond what we're going to cover in this class.